Okay, so let's discuss what it the criteria for designing the mechanical spring, especially for the compressive spring. Okay, so we have to take into account the stability and critical frequency or number of active coil, feet of Murray, and what is the Z vector and spring index and so on. So those are things that we have to take into account for designing a mechanical spring. Okay, so for example, uh, what the parameters that we have to consider in the very beginning is okay, what type of the a spring that we have to select it. So what is spring rate or a spring constant K, right? So based on the materials property and the dimension and geometry. So the K can be defined as the uh, dimension related, right? And the materials related, right? So the K can be in terms of the wire diameter or the mean coil diameter and the shear rigidity and the active coil number and so on, right? So that's the first thing you have to consider. What's the materials property and what's the dimension or what's the geometry of this spring that we have to select it. Okay. And the second is what's the stress, the shear stress, right? When this mechanical spring is pressed, so there's the shear stress, the torsional shear stress and the pure shear stress, right? Applied to its cross section. Okay. Therefore, we can define the shear stress equals to a constant KB, right, times this term, and KB is defined in terms of the spring index C, right? C, spring index. Okay, so if this mechanical spring is subjected to a static loading, which means the force is a constant, right? It means force is constant, right? So in this case, while we can easily define its materials property to find the parameters A and M, which are materials related, right? Which is materials related. And then based on these two parameters, we can find the tensile strength. Okay, and also we can define its torsional shear yielding stress, SSY, okay, which is a percentage of SUT, and SUT we already find it here. Okay, okay, if this force, if this mechanical spring is subjecting to the cyclic loading, or we say the fatigue, now we have to recap what we learned from maybe the previous semester, right? So what's the criteria, fatigue criteria that we use, right? So in this case, we have to figure out what is the, we say the mean force and alternating force, and what is the mean shear stress, and what is the alternating shear stress, right? So we have to find its torsional shear yielding, which is a percentage of SUT, right here. And this spring wire might be processed with pinning or unpinning. Okay, that's mean its surface has been treated by pinning or unpinning. Okay, and because of the fatigue loading, the cycle loading apply, so we'll have to take into account the say the SSE, which is the endurance limit, or say the shear endurance limit, which is a function of SSM, SSA, and SSU. SSM represents the shear mean stress, okay, shear mean stress. and S is Y represents the alternating shear stress. Okay, and so on, so on. Okay, so the spring index equals to the mean core diameter divided by the wire diameter, right? And usually that's why I mentioned previously the C in a range between 4 to 12. Okay, if the smallest with the C is small, which means the high wire diameter and the low mean diameter. So this spring where it has the stress applied to it, which the inner fiber is subjecting to the compression, and the outer fiber is subjecting to the tension. Okay, and in this case, the C is less than 4. Okay, it's less than 4. And if the C is greater than 12, that means the springs are easily to individual packing. Okay, and causes an additional cost. Okay, so that's mean the C is greater than 12. That's mean the low D and the high mean core diameter, right? So that's mean we have the like this. Okay, okay, and it is easy to individual packing. Individual packing. Okay, okay. So the number of active coil. So if you still remember the table that we look at the previous course, right? So there's a table to define the active coil number based on the end condition, the spring's end conditions. Okay, and usually the number of active coil is between 3 to 15. Okay, 3 to 15. And there is a fabrication issue that we have to consider is that uh, if the pitch of the spring is not, I mean, a pitch between, or say the pitch within this mechanical spring, they are not equal. That's mean, okay, so if this P1, the pitch one does not equals to pitch 4, or does not equal to the pitch 2 or pitch 3. What's that mean? That's mean there is a linearity issue, right? So that's mean when this spring is subjecting to a compression, the deflection is not linear with the force applied, right? So it's not a linear behavior anymore. If the P1 does not equals to P4, okay? If the P1 does not equal to P4 or does not equal to P2, okay? So there's the linear issue here. Okay, therefore the force does not equal to Ky. Okay, it's not equal to Ky. Okay, and usually we define the maximum force applied to the compressive spring is less than 7/8 times the solid length force. Okay, solid length force, that means we apply the force which to solid spring. Okay, solid spring. So for the safety issue, the maximum force should be less than the solid length force. And we define it as the 7/8 of the solid length force. Okay, and it is the restriction for service. Okay, it's a restriction for service. Okay, and therefore we can replace the force. The force, okay, the force term in the maximum, or the force term in the shear stress, right? The force term in the shear stress here, okay? The force term in this shear stress, okay? And replace it by what? Right here, right? Fs. Usually we define as Fs. However, here we usually use the Fmax. Okay, Fmax. Okay, for the safety issue. Okay. And when we define the safety vector, this safety vector, like the suppose like NS, usually is equal and greater than 1.2. Okay, 1.2. And we use the solid length force to define the safety vector. Okay, we use the solid length force to define the safety vector. Okay. Okay. So the figure of merit, FOM presents the relative cost materials times the mass of the spring. Okay, so we can define the figure of merit equals to the relative cost times the gamma, which is specific weight, right? Times the pi d squared over 4, right? And times the pi times the number of the active coil times the mean spring diameter. Okay. So when we can rearrange this term, right? So we got this FOM, figure of merit, equals to the relative cost times, okay, gamma pi square d square nt times the capital D divided by 4. Okay, divided by 4. Okay, and the stability of the spring. So if you guys still remember the buckling in your materials mechanics course, we know for this the long and the thin and the slender beam, right? Where we apply the force, we apply the actual force. And maybe this force, which is not beyond its materials limit, like the yielding stress. However, because this beam is slant enough, thin enough, so when there's the impact from the side, or there's a force applied from side, and it might be buckled. Okay, it might be buckled. So similarly, this behavior occur in the mechanical spring, or say the compressive spring. Okay, so if you guys still remember, for a column, right, we have the critical load, right? It equals to the C, the constant, which depends on the end condition of this beam, or this member, this component. Okay, times the pi E times the I over L, right? Square, and this I is defines the radius of gyration. Okay, and L over R. Sorry, the R defines the radius of that gyration. Okay, and I is the polar inertial. Okay, and L over R is defined as the slenderness ratio, right? And the constant C depends on the end condition. Okay, so those analysis is based on the beam with the actual loading to cause buckle, right? To cause buckle. So if now we just think of replace this beam or replace column by a springs. Okay, by springs. Okay, by springs. Okay, and we define its critical deflection equals to this term. Okay, and also there's the lambda EFF, which is the effective slenderness ratio of spring. Remember, we have the slenderness ratio of a column, and we have the effective slenderness ratio of springs, okay, which equals to alpha, and which can be related, or which can be correspond to the C, right? The end condition times the L naught, with the free length divided by the mean diameter, okay, the mean diameter, okay, the mean diameter, okay, the mean diameter. Okay, and the Y max, the maximum deflection in Y direction, equals to the L naught, the free length, minus the solid length, right? The free length, right? Minus the solid length, right? So, and the difference as the Y max, the Y max, right? And this Y max has to be smaller than the Y critical. Okay, have to be smaller than the Y critical. Okay, so the Y critical here. Okay, so there are two parameters, C1 prime and C2 prime, which are related to the material's property. So the C1 prime equals to the E, the Young's modulus over 2 times the E minus G, the shear rigidity, and C2 prime equals to 2 pi squared times the E minus G over 2G plus E. Okay, so these two parameters are related to the material's property. Okay, so if the C2 prime over lambda EFF squared is greater than 1, okay, if this term is greater than 1, what's that mean? This term is greater than 1. It can be represents the stability, which is the absolute stability. Okay, so this is the condition for the absolute stability. Okay, that means the C2 prime have to greater than the lambda EFF square. So if this condition reached, that means this spring is absolutely stable. Absolutely stable. Okay, absolutely stable. Okay, and then we can plot the those materials property, right, in the C2 prime, right? So the C2 prime, right, here, right, and the lambda EFF, the effective slenderness ratio, right here, right, right here. So we can rearrange this equation. We can rearrange it, right, to get the L naught, the free length for this for if this spring is absolutely stable, it has to meet the condition that is the L naught, the free length has to be smaller than this term, right? And if the spring is made of the steel, right, usually made of steel. So we know the materials property of the steels is shear rigidity and the Young's modulus, right? So we can simplify this to a simple relation between the free length and the mean diameter and the end condition. Okay. Okay, so there are other effects like the surge failure, which is related to the force frequency, which equals to the whole number times the nature frequency. Okay, it's the nature frequency of the spring. Okay, and the W is the weight of the active parts. Okay, active parts, and the K is the spring constant, and the G is acceleration. Okay, I'll say just the gravity. Okay, the gravity. Okay, so there's one example. Maybe I just show you this one examples here. Okay. Okay, for the plane end, okay, so we already know what's the end condition, and we know what's this wire is. Okay, what the wire is. Okay, and the Y, the deflection, right? The deflection when applied force is 18 pounds, and the force to the solid length, okay, the solid length force is 24 pounds. Okay, okay, and we define the safety vector has to be greater than equal to 1.2. Okay, 1.2. And the definition of the safety vector equals to the SSY, the torsional shear yielding stress, divided by the maximum shear. Okay, the maximum shear here. Okay, and what we need to solve is what's the lowercase uh the wire diameter, what the wire diameter is. Okay, what the wire diameter is. Okay, so let's look the process of this question. Okay, so here there's no mention of the pretension, or we say the presetting process. Okay, therefore can define as SSY, the torsional unit stress equals to 45% of SUT, and the SUT is a function of the parameters A and M, right? So which can check the table, right? We can check the table to find these two parameters, okay? Okay, for this materials. So we can find that A is 140 and M equals to 0.19, okay, equal to 0.19. Okay, so for this music wire, so we got this before set removal whose SSY, okay, SSY. And for this hydro wire, as exponent M equals to 0.19 and A equals to 140, okay, 140. Okay, so you got these two numbers, okay, and the maximum shear equals to the SSY divided by the safety vector, okay, safety vector, okay, and the KB, the shear stress KB, or sorry, the maximum shear K that equals to KB times this term, right? Okay. Okay, so this maximum shear equals to the point 45% times A over d to the power of m divided by the safety vector. Okay, divided by safety vector. Okay, and we can rearrange the capital D over the lowercase dq by the spring index, right? The spring index here. Okay. Okay, so finally we get the finally we get the d of the power 2 minus m, right, equals to the d squared divided by the d power of n. Okay, we can rearrange this equation to get this. Okay, therefore, the ratio of this term will equals to this term, right? So we find, of course, we know the KB, right? We already know that, and the wire diameter, right? And the spring index. Okay, the spring index here. Okay, so it's 3 KB, lowercase d, the wire diameter, and the spring index. Okay, so the questions already tells the Y deflection with the force 18 pounds. So we can find the spring constant, right, equals to the spring constant, the function of this material's property and the dimension. Okay, so we can get the number of active coil, right? Number of active coil. Okay, so the K equals to this term, right? So we can get the number of active coil. And we already know F the spring made of the steel, right? So the condition for its stability, if this spring is absolutely stable, you have to make this requirement, right? Right, you have to make this requirement. Okay, and the L naught, the free length equals to solid length plus the Y max, the maximum deflection, equals to the LS solid length plus the FS over spring constant. The FS equals to 24, right? 24, the problem tells us, and the K equals to 8, right? So we got the L naught equals to the LS plus 3, okay? Okay, so now we can just use the Excel or whatever the tools, the computer tool that you use it, right? So we can figure out what is the limit number of coil, the number of active coil. Okay, so we can just try the KB, the lowercase d, capital D number of coil. So when this uh spring index equals to 10.5, and this NA is greater than 15. Okay, it's beyond what's the design criteria of the compressive spring. Okay, so what we can select is that the number of active coil less than 15, right? So in this, we can select the C equals to 11, 11.5, and 12, and so on. Okay, and so on. Okay. Okay, so any questions? Okay, and then we check the table. So we have to select the spring, right? We have to select the spring, which these springs that we can use it, right? So the lowercase d is about 0.1055, okay? 0.1055 should be between these two, right? Here, between these two. 1.055 here. Okay, so the name of the god should be 12 or 13. Okay. Okay, so we should select these two springs with the wire diameter equals to 0.0951 or 0.1055. Okay, in this case, C equals to 11. Okay, and right, right, these two and these two, this is meet our requirement. So in this case, maybe this is quite suitable for our application or suitable for the description of the questions, right? Okay, so suppose we choose this 12, gauge with the D equal to 0.1055, and the spring index equal to 11, and the mean spring diameter, mean core diameter equals to 1.16. Okay, 1.16. Okay, 1.16. So we know the C, the spring index, and we know the diameter, right? And then we can plug those number to here, right? And we know the shear rigidity, can plug in here. And finally, we get the number of coil. The number of the active coil is 15.25, right? So let's go back to this Excel table. Let's look into whether it is okay. So yeah. So maybe within this, right? It's correct, right? And for its critical deflection, okay, it's critical length for the stability issue. The L critical has to be equals to 2.63 times D over alpha, right? And the L naught, right? L naught, as we already find that L naught equals to LS solid length plus 3, right? Okay. And the L naught equals to 4.61. Okay, equal to 4.61. Okay. Okay, and the safety vector, it defines the SSY over the maximum shear stress, right? Because it is before set removal, right? So it's 45%, right? 45%, and we can check the table to find the number. And we know the wire diameter, right? Wire diameter here. And we know the FS, the question already tells us, right? 24. And the mean core diameter is 1.16, right? So finally, we can get the safety vector equals to 1.426. Okay. 1.426. Okay, and if we select the other spring with the this Y diameter is 0.959, we will get the lower safety vector. We will get the lower safety vector. Okay. Okay, so this is what we already know. The springs, the buckling. Okay, the buckling. So I'll skip it. So in this case, it's the for very the high spring index. Okay, the high spring index and this very low spring index. Okay, in fact, the low spring index has been, as I mentioned previously, here, right? It's the small c, right? A small c. It's the high D and the low capital D, right? Which is the case, which is not easy to buckle, okay? Which is not easy to buckle, okay? And for the high C, well, it's easy to buckle, okay? It's easy to buckle for a spring, okay? For a spring. Okay, so I'm gonna stop here. So there are other design methods. Well, it's similar to what we learned previously. Okay, I think you guys can just review my slide. Okay, to define these parameters for designing the mechanical springs. Okay.